Hello, this is the Mark T. Sheehan STEM Team IPR2 presentation. So for this, I got the joy of redesigning our landing system. So first of all, we realized that we made a miscalculation last time and changed out our previous shock absorbers with a telescopic shock absorber so that we can extend it out outside the starting volume a lot easier. We kept our nice rubber feet there, as well as the rubber feet to protect it as the second system in case these fail. At the top, we added a connection in between our two shock absorbers so that we could transfer the force going up through them into mechanical stress. And just a note, this is half of the design. It would have 4 legs on it, but this is just to make sure that it's a lot easier to see. To extend our telescopic shock absorbers, we have a hydraulic system to make sure that they get pushed out. And right here, we added a nice little locking system to make sure that once we extend these out initially, they get locked into place nicely. The Sheehan STEM team has compiled the finalized list of requirements provided both by Sikorsky and by NASA that are relevant to the development of our landing and tracking assembly. That full list is going to be attached in a separate document. We then took those finalized requirements and used them to analyze our subsystem 1, which is our landing gear. In particular, we focused on the SC02 requirement that the system must stay within the frame perimeter of the challenge rig during the trip to Mars, which inspired our telescoping legs that have the shock absorbers on them in order to get the shock absorbers past the bottom of the frame perimeter. In addition, our team ensured that this subsystem should be able to operate autonomously and plan subsystems 1 and 3 so that they will be able to correct for any problems that might emerge from a catastrophic event without additional safety systems.
So the programming team used the potentiometer as an analog input in order to create a digital output of a blinking LED. And yeah, with this experience, we'd be able to use different sensors in order to help map out the terrains in future projects.
In addition to preparing to program and design circuitry for further challenges with the analog sensor code, the programming team has also planned the models that we're going to use in order to collect and analyze data to determine a landing location for the rotorcraft. The 2 major challenges that we face in doing so are determining where the rotorcraft is in its tracking path, and then using all of the data that we collect to determine a landing location. Our team is planning on using an infrared sensor to determine the distance between the rotorcraft and the ground. We want to pair that with the location of the rotorcraft to determine where to land. We're going to determine where the rotorcraft is based on either position sensors that we would have to get approval for, or by parametrizing the path in terms of time, which we're favoring as the more simple option. Once we collect all the data from the infrared sensor combined with location, we're going to use that data to determine where we're going to land by looking for flat surfaces, either by finding an area where the sensor data is of low variance, or by pooling the data to create a smaller 2D image to analyze, or using a convolutional neural network.